Welcome back to Plus 2 Chemistry class. We were studying about P blocks elements in detail. Last class we discussed the introduction part of group 15 elements: nitrogen, phosphorus, arsenic, antimony and bismuth. Okay, today we will study the rest of the part of that group 15 and we will conclude the chapter with certain elements and its uses and properties. So let's start. Ammonia can be prepared from nitrogen compounds. Okay, by the decomposition of nitrogenous organic matter we can prepare ammonia. This is NH2CONH2. What is this? It is urea. Okay, NH2CONH2, urea with water will give you ammonium carbonate, and ammonium carbonate reacts to form ammonia plus H2O plus CO2. This is the normal method or the natural method of preparation of ammonia. By the decomposition or by the decay of nitrogenous matter, ammonia will be produced. Okay, no energy is required here. Urea, when it decomposes, you will get what? Ammonium carbonate, and on further decomposition, ammonia will be obtained. In the laboratory preparation, ammonium salts are usually used. Okay, laboratory or in the small scale preparation of ammonia, we can use ammonium salts. What are ammonium salts? Mainly ammonium salts are ammonium chloride and ammonium sulfate. Okay, ammonium chloride will react with calcium hydroxide. Calcium hydroxide is caustic soda. Caustic soda to form ammonia. Okay, caustic soda and ammonium chloride in a laboratory condition will react to form ammonia. Similarly, ammonium sulfate plus sodium hydroxide also react to form 2NH3 plus 2H2O plus sodium sulfite. These are the main laboratory preparations from ammonium salts. Simple preparation. Next, the main method of preparation we studied. It is Haber process. N2 plus 3H2 will react under high temperature to obtain what? Ammonia. Okay, N2 plus 3H2 gives 2NH3. This industrial method of preparation by Haber process is a reversible reaction. Look at the arrow, it's a reversible reaction. According to Le Chatelier's principle, higher amount of pressure, okay, higher amount of pressure will favor ammonia or ammonia formation. Okay, if there is no higher amount of pressure, reversible reaction will happen. Okay. As soon as ammonia is formed, it reversibly goes as nitrogen and hydrogen. Okay, only under high pressure, according to Le Chatelier's principle, you studied in equilibrium, isn't it? Formation of ammonia takes place, or forward reaction happens only at higher pressure. So, the optimum condition for the formation of ammonia is very important for you to study. What are the optimum conditions? Pressure is 200 into 10 raised to 5 Pascal. Okay, or 200 atmospheric pressure. 200 into 10 raised to 5 Pascal is the optimum pressure required for the formation of ammonia. Second, temperature, approximately 700 Kelvin temperature. We studied 773, isn't it? Approximately a 700 Kelvin temperature is required for the formation of ammonia, and the formation constant in Haber process, that is N2 plus 3H2 will give 2NH3. This reaction has a formation constant value of minus 46 kilojoule per mole. This is the formation constant value. Okay. For this reaction to take place, a catalyst is required. We studied in our D block chapter, D and F block chapter, Haber process catalyst, isn't it? It is a D block metal, that is iron oxide. Okay, iron oxide FeO is a catalyst in what? It is a catalyst in the preparation of ammonia in Haber process. That is, it lowers the activation energy required for the formation of ammonia. With the iron oxide, small amounts of Al2O3 and K2O are also used. Earlier, in the preparation of ammonia by Haber process, iron oxide and also molybdenum metal, okay, MO, molybdenum metal is used as a promoter, but now iron oxide plus small amounts of Al2O3 and K2O are used, but earlier with iron oxide, molybdenum is used as a promoter for the reaction to take place. Okay, it's used as a promoter. These are the main preparation methods for the formation of ammonia. First is the natural preparation from the decomposition of nitrogenous matter. Next, from the ammonium salts, that is the laboratory preparation. And third is the industrial preparation, that is the Haber process. Now we will discuss the properties of ammonia and also the uses. As you all know, ammonia is a pungent smelling gas. It is a colorless pungent smelling gas. Ammonia, the boiling point is 239.7 Kelvin and freezing point is 198.4 Kelvin. These are the boiling point and freezing point of ammonia. Okay, I just mentioned it to show you that the high values of melting and boiling point for ammonia. Why is it so? Because of the formation of hydrogen bonds with water. Okay, ammonia has high melting and freezing point due to their formation of hydrogen bonds with water. It has high melting and boiling point. And also it's highly soluble in water. Ammonia is highly soluble in water. And the equation is what? NH3 plus H2O will give you NH4 plus ammonium ions. Okay, it is ammonium ion plus OH minus. It is highly soluble in water due to its formation of hydrogen bonds with water. Ammonia forms hydrogen bonds with water and it is highly soluble in water. And we know there occurs the formation of what? OH minus when ammonia dissolves in water. So we can say ammonia as a weak base. Okay, ammonia is a weak base as it dissociates to form hydroxide ions. Ammonia is considered as a weak base. This is the next point. Now, look at the structure of ammonia. NH3. 3 hydrogen bonds and also 1 lone pair is present for ammonia. This is the structure of ammonia. 3 hydrogen bonds, 3 NH bonds are there and 1 lone pair in the nitrogen. Okay, the bond length, NH bond length is 101.7 degree or 101.7 picometer and the bond angle is 107.8 degree. Okay, bond angle is 107.8 degree and bond length, NH bond length is what? 101.7 picometer. Okay, its structure or the geometry is what? Trigonal pyramidal. Trigonal pyramidal. You have already studied VSCPR theory, isn't it? NH3 geometry is what? Trigonal pyramidal. And it has 1 lone pair and 3 bond pair. Okay, this is 1 bond pair, the second bond pair and the third bond pair. 3 bond pairs and 1 lone pair for ammonia. This is the structure of ammonia. Look here. Here nitrogen forms 3 bond pairs with hydrogen and there is 1 lone pair for nitrogen and the geometry is trigonal pyramidal. Okay, ammonia reacts with water to form hydroxide ions or dissociate to form hydroxide ions, so it is weakly basic or a weak base we can say. And ammonium salts reacts with acids. Okay, it forms ammonium salts when it reacts with water. When ammonia reacts with acids, okay, when ammonia reacts with acids you will get ammonium salts. Ammonia reacts with acids to obtain ammonium salts. Okay, when ammonia reacts with HCl you will get ammonium chloride, NH4Cl. Similarly, when ammonia reacts with sulfuric acid you will obtain what? Ammonium sulfide. That is, ammonium salts are obtained when ammonia reacts with what? Acids like hydrochloric acid, sulfuric acid, etc. This is one of the important point. Ammonium salts are formed when ammonia reacts with acids. Okay. Next thing is what? Ammonia acts as a Lewis base. Okay. Why ammonia acts as a Lewis base is an important question. Why? Due to the presence of 1 lone pair on nitrogen, ammonia acts as a Lewis base. Okay, Lewis base. It's a Lewis base. Why? Because the lone pair on nitrogen, look here, the lone pair on nitrogen is donated to other metals, and there you can form what? A bond. Look here, zinc sulfate plus ammonium hydroxide will give you zinc hydroxide plus ammonium sulfate. This is the first reaction. Second one is what? FeCl3 aqueous, ferric chloride and ammonium hydroxide. Ammonium hydroxide reacts with zinc sulfate to form what? Zinc hydroxide and ammonium sulfate. Similarly, ferric chloride FeCl3 reacts with ammonium hydroxide to form what? A complex. This is what? Fe2O3 dot XH2O. They are hydrates. Okay, hydrates. Water hydroxides or hydrates we can say. And Fe2O3 XH2O plus ammonium chloride is formed. We studied ammonia acts as a Lewis base, isn't it? Because lone pairs on the nitrogen is donated to other atoms. Here, ammonia reacts with copper and forms a complex CuNH3 4 times 2 plus. Here, this nitrogen, lone pairs on the nitrogen forms a linkage with the metal copper. Okay, it is CuNH3 4 times. NH3 and NH3. Copper forms a linkage with the lone pairs on the nitrogen and forms a complex. This is CuNH3 4 times 2 plus, and it is what? Deep blue in color. Copper here, this is an example to show how ammonia acts as a Lewis base. Lone pair on the nitrogen is shared with copper metal and forms a linkage, and it forms a complex that is deep blue in color. Similarly, Ag plus plus Cl minus will give you AgCl, which is a white precipitate, isn't it? Silver with chlorine will give you silver chloride, that is a white precipitate. Silver chloride also reacts with ammonia. Silver metal forms a linkage with ammonia, that is AgNH3 twice Cl, and this is also a complex which is colorless. These are some of the examples to show the Lewis base nature of ammonia. Okay, this is also used for the detection of metals like silver and copper. Okay, copper ions, Cu plus ion and Ag plus ions. Okay, Ag plus ions can be detected. How? Okay, when a metal solution is given, to check whether copper is present in that, what we will do? We will add ammonia. If copper is present, there a complex will be formed and color change occurs mainly. Deep blue color will be formed. So we can identify the presence of copper in that. Similarly, when a solution is given, to check whether it contains silver or not, what you can do? You can add ammonia to that. When that solution changes to a colorless solution, we can detect the presence of silver in that metal solution. Also, for the detection of metals, we can use these reactions. These are the main reactions of ammonia. Now let's study the uses of ammonia. What are the important uses of ammonia? Mainly, ammonia is used for the preparation of fertilizers containing nitrogen. Okay, nitrogenous fertilizers like urea, ammonium nitrate, ammonium sulfate, etc. are used in fertilizers. For their preparation, ammonia is mainly used. The next use is what? For the manufacture of inorganic nitrogen compounds. Inorganic nitrogen compounds manufacture, we use the compound ammonia. For example, for the preparation of nitric acid, HNO3. It is a nitrogen compound, isn't it? For nitric acid preparation, we use ammonia. That is the manufacture of certain inorganic nitrogen compounds. And the last use that we need to study is about liquid ammonia. Okay, liquid ammonia is used similarly like that of liquid nitrogen. Dinitrogen is used as a refrigerant for preservation. Isn't it? Similarly, liquid ammonia is also used as a refrigerant. These are the main uses of ammonia. We studied the preparation methods, industrial preparation, laboratory preparation, and also the main properties of ammonia and also uses we discussed here. Nitrogen forms oxo acids like hyponitrous acid, nitrous acid, and also nitric acid. Hyponitrous acid is H2N2O2, then nitrous acid is HNO2, and nitric acid is what? HNO3. Among these oxides of nitrogen, the most common and commercially used oxide is what? Nitric acid. Okay, and its preparation we studied. What is that? From ammonia. Okay, the commercial preparation of nitric acid is mainly from ammonia, or in the use of ammonia we studied it, isn't it? Now we are going to study in detail about the preparation of nitric acid, properties, the structure of nitric acid, and also the uses. Nitric acid is mainly prepared in laboratory preparation from sodium nitrate or potassium nitrate. Heating potassium nitrate or sodium nitrate with sulfuric acid will give you nitric acid plus sodium hydrogen sulfate, NaHSO4. Okay, the laboratory preparation is the heating of sodium nitrate or potassium nitrate with sulfuric acid. Next is the preparation or the industrial preparation. Industrial preparation of ammonia is Haber process. Similarly, for the industrial preparation of nitric acid, we have a method, and the name of that is what? Ostwald's process. Okay, the name is important. It is Ostwald's process. In multiple choice questions, you may have options like preparation of ammonia, the Haber process, Ostwald's process, etc. Okay, so it is important to study the name. It is Ostwald process is the preparation of nitric acid. In that, the first step is what? The catalytic oxidation of ammonia by atmospheric oxygen. Catalytic oxidation means a catalyst is used for the oxidation of ammonia. Okay, ammonia reacts with oxygen. Catalytic oxidation, that is from air. Okay, this is oxygen is the air. And the catalyst used here is, it is also important, platinum or rhodium we will use, RH. Platinum or rhodium is used here as the catalyst in Ostwald process. Okay, the catalyst used in Ostwald's process is what? Rhodium or platinum to form nitrous oxide plus H2O. That nitrous oxide formed combines with oxygen to form NO2. Okay, nitrogen dioxide, NO2. Ammonia under catalytic oxidation in the presence of rhodium or platinum will give you nitrous oxide, NO, and that reacts with oxygen to form NO2. Further, this NO2 dissolves in water to form HNO3. Okay, this is a gas, NO2 gas, or this is also a gas. That gas, NO2 gas, dissolves in water to form HNO3, nitric acid plus NO. These are the three main steps. First step is what? Catalytic oxidation. Second is the combining of oxygen with NO, and the third step is what? The formed NO2 dissolves in water. These are the three main steps in Ostwald's process. Okay, we got nitric acid, what we needed, isn't it? Plus NO. This NO we will recycle. Okay, remove the impurities of this NO gas and we will reuse in this same reaction. We require MNO here, isn't it? This is recycled and used, and this HNO3 will be purified and also concentrated by distillation and also by dehydration with sulfuric acid. Okay, the remaining or excess amount of water from the nitric acid will be removed by dehydration, and also it is purified with the process of distillation. So we will obtain pure nitric acid. These three steps are important, and also the name, that is Ostwald's process. Study the equation and the steps. Now regarding the property of nitric acid. Okay, nitric acid is a colorless liquid and also a pungent smelling gas. Okay, usually stored in glass bottles. That is the main physical property. It is a colorless liquid. Okay, nitric acid. And in gaseous state, it is usually what? A planar structure. And the structure is drawn here. The planar structure of HNO3. It is like this. In gaseous state, it is planar. Look here. The bond length, NO bond length is 140.6 picometer. NO here, this bond, okay, it is 121 picometer. Both this NO bond length is 121 picometer. ONO bond angle is 140 degree and HON bond angle is 102 degree. Okay, this is the structure of nitric acid. You may get different options regarding the structure of nitric acid in planar state, and you may be asked to find which is the correct structure. So study the structure, planar structure of nitric acid in its gaseous state. In aqueous solution, HNO3 or the nitric acid acts as a strong acid. In aqueous solution, it acts as a strong acid. The equation is what? HNO3 plus H2O will give you H3O plus NO3 minus. Here hydronium ion. Okay, this H3O plus is called hydronium ion. When nitric acid reacts with water, hydronium ions are produced, which indicate that it is what? A strong acid. Nitric acid is a strong acid because hydronium ions are produced when it reacts with water. Next thing, okay, the reaction of nitric acid or the products of reaction with nitric acid depends upon the concentration. Okay, what product is obtained when nitric acid reacts with metals depends upon the concentration of the nitric acid. Okay, the products will vary according to the concentration of nitric acid. Look here, the metals, these are the examples of metals, how metals reacts with nitric acid. Okay, as nitric acid is a strong oxidizing agent. It undergoes or it helps in oxidation. So, it is a strong oxidizing agent. Nitric acid is a strong oxidizing agent. Okay, hydronium ions are produced. So, it acts as a strong acid. Let's look the case of metals. How the concentration varies and the products also varies. Copper metal, when it reacts with nitric acid and the condition here is dilute. Okay, copper with dilute nitric acid will give you copper nitrate CuNO3 twice plus 2NO plus 4H2O. Similarly, when copper reacts with nitric acid and in a concentrated form, okay, nitric acid here is concentrated. Product is similarly copper nitrate plus 2NO2 plus 2H2O. Okay. So, the question will be like, when dilute nitric acid reacts with copper, what will be the product? You will have many oxides, nitric oxide, nitrous oxides, hyponitrous oxides, etc. Okay. When it reacts with dilute nitric acid, the product is what? NO. Okay, nitrogen oxide, the product is what? NO. But when copper reacts with HNO3 in a concentrated form, okay, when concentrated nitric acid reacts, the product is what? Nitrogen dioxide. It is NO2. This is the main difference. Okay, when dilute nitric acid reacts with copper, NO is obtained, and similarly when concentrated nitric acid reacts, NO2 is obtained. Okay, like this the multiple choice questions will be asked. Okay, next regarding zinc metal. Zinc, when it reacts with HNO3 in a dilute form, you will obtain N2O. Dinitrogen oxide is N2O, and when it reacts with concentrated nitric acid, the product is what? NO2, nitrogen dioxide. Okay, study this equation and also the difference. Here when dilute nitric acid obtained, you will get N2O. When concentrated nitric acid reacts, you will get NO2. Okay, these are the main important reactions. Like metals, nitric acid also oxidizes non-metals. For example, iodine is oxidized to iodic acid, carbon to carbon dioxide, sulfur to sulfuric acid, and also phosphorus to phosphoric acid. Let's look into the equation. Iodine I2 plus HNO3 will give you iodic acid. Okay, this is iodic acid. Iodine when oxidized with nitric acid will obtain what? Iodic acid plus NO2 plus 4H2O. Carbon is oxidized with nitric acid to obtain carbon dioxide. Sulfur to sulfuric acid. Similarly, phosphorus to phosphoric acid. These are the examples for oxidation reactions of nitric acid with non-metals. Next, the other important thing is what? The uses of nitric acid. Okay, the first use is in the manufacture of ammonium nitrate. Okay, ammonium nitrate is a main component of fertilizers, nitrogenous fertilizers. Okay, for the manufacture of ammonium nitrate, nitric acid is used. Okay, and also in the as a nitrate, okay, as a nitrate component in explosives and pyrotechnics. It will give a nitrate component. It will act as a nitrate component in explosives and pyrotechnics. Next, for the preparation of organic nitro compounds, okay, many organic nitro compounds are there. For their preparation, nitric acid is used since it is a strong oxidizing agent as an organic nitro compound. Also, the other two uses are the oxidizer in rocket fuels and also etching of metals. These are the important uses of nitric acid. Here the main important thing is what? The oxidation reactions of metals and also non-metals. What are the products? The structure of nitric acid in gaseous state and also the preparation methods. The industrial preparation method is what? Ostwald's process. These are the important points regarding what? Nitric acid. That's all, dear students. I hope you understood. If you have any doubt, you can comment below. Thank you and have a nice day. Happy learning.